Good morning, Miss Saigon. No, that's from an old movie. Anyway, today we're going to start talking about Newton's laws of motion. We've really been dealing with them for a few weeks now, but today we're going to begin to look specifically at what Newton said, and it should make a lot of sense because of what we've been working on over the past few weeks in terms of motion and balanced forces and all that stuff, friction and so on. So let's go ahead and get started and see where it takes us. So Isaac Newton, so when we say Newton's laws of motions, we're talking about the Isaac Newton. Hopefully you've heard of him. But he was around in the 17th century, so that would have been like that would have been like the 1600s. And he, of course, was a scientist. And he came up with a way to describe motion using three laws. And to this very day, we still use those three laws. They still make sense to us as, and they still make sense of what we find and what we observe happening naturally when we talk about motion. So we're going to talk about his first law today. So let's have a look-see. So there's a little video that I want you guys to watch. So go ahead and watch this, and we'll come back and continue from where we left off. Okay, so hopefully you watched the video. You were only needed to watch the first 22 minutes and 34 seconds of that video, at least for now. When we talk about the second law of motion, we may finish watching that. There's only about 5 minutes left. The gentleman in the video talks for a much shorter period of time about the second law of motion, but it's not as intricate and not quite as confusing, perhaps, as the other one. I'm going to turn the light on so maybe you can see me a little bit. All right. Now let's talk about this. So an object at rest stays at rest according to Newton's first law. Newton's first law also tells us that an object in motion will stay in motion with the same speed and in the same direction as that net force, unless it's acted upon by an unbalanced force, which you should know very well about because we've been talking about that. So I want you to take a look at one more video. This one's a much shorter video and pretty cool too. So go ahead and pause this video and watch the Questlab airboard video. Alright, so you got to see the hoverboard. That's pretty cool. And he talked about Newton's first law and his second law, but we're going to dissect the first law a little bit further, because I want to point out to you that there are really two parts to the first law. The first part predicts the behavior of stationary objects, and the second part predicts the behavior of moving objects. So it's kind of a pretty intricate law in the sense that it deals with two different conditions, or two different stages, or I guess you could say conditions. But we have a conditional statement that comes next. But before we get there, let's look at these two these two different portions of the law. The first is that objects at rest tend to stay at rest. And so in this diagram you can see that there are some mathematical equations involved here. And what this is telling us is that velocity is at 0 meters per second, right? So that would make sense because the object is at rest, it's not moving. And acceleration also equals 0 meters per second squared. So mathematically speaking, if you multiply 0 and 0 together, or add them together, or subtract them, or do anything with them, you're still going to get 0. So mathematically, it would seem appropriate that objects at rest at a velocity of 0 with 0 acceleration are going to continue their velocity of 0, which means they're not even moving. But when you have objects in motion, you have to have a velocity that's anything but 0 meters per second. But your acceleration can equal 0. You don't need to add any more acceleration to it. And that object, given that there would be no friction, would be able to stay in motion. So it would be the same speed and would continue going in the same direction. So if you think about objects in space, it's probably even easier to imagine. Or if you think about the hoverboard video that you just watched, you know, in space, we pretty much know that if you give something even a gentle push, it'll start floating through space and literally, well, there is a little bit of friction in space, so eventually it probably would stop, but it would take a very, very long time. It would be hard for the little amount of frictional force in space to overcome the inertia of whatever object you just pushed into motion. All right. So at the end of Newton's first law, there's this condition where it says unless. So an object at rest stays at rest unless the object is acted upon by an unbalanced force. Or you can take the other side of the equation. An object in motion tends to stay in motion unless the object is acted upon by an unbalanced force. So friction would be an unbalanced force that causes an object that's in motion to stop moving. Okay. So that should hopefully make sense to you. Another way to think about this is to say, as long as the forces are balanced, the first law of motion applies. Okay? Unless. That's the condition. And Newton was smart enough to realize that the rule worked, but there was an exception to the rule, and that's when an unbalanced force comes into play, a net force, if you will. So if that doesn't come into play, if that clause, if that exception doesn't come into play, if there's not a net force or an unbalanced force, then the objects will accelerate continually. They'll increase or decrease their speed of motion. All right. In the first video, you saw the gentleman in the video talking about what happens when you go around the corner in a car, or when you stop suddenly, or when you get hit from behind suddenly and you're sitting in a car. On your worksheet, there are some spaces for you to make predictions. So imagine you're carrying a tray of water and you're walking around a track that has very sharp corners in it. So it's not a great big oval track like you would see at a race, but this is a track that has sharp bends. And if you were to move quickly to go around those corners, what would happen to the water? So make some predictions based on the scenarios given, and basically guess what's going to happen to the water, and then we'll go on from there. So go ahead and pause the video here, and we'll pick it up as soon as you're done. Okay, so your first prediction on the worksheet is starting from the starting line. So the question is, if you filled up your baking dish and you had water in it all the way up to the rim, you walked around an oval track making an attempt to complete the lap in the least amount of time possible, what would happen to the water? So when you're at the starting line and you begin to move, what would happen to the water? Well, before you start to move, the water's at rest. When you start to move, the water wants to stay at rest. So you move and the water stays in place, and you basically walk into the water and you get wet. Hopefully that was your prediction as well. And let's look at the second one. You get to the finish line and you stop suddenly because there's a reporter right in front of you, so you have to stop. Well, the water at that point was in motion, so as soon as you stop, what's going to happen to the water? Well, that water is going to want to keep moving because objects in motion tend to stay in motion unless there's an unbalanced force applied. So you stop, you're holding onto the tray stops with you, but the water wants to keep moving forward because that's the motion that it was already in. So it goes forward and splashes on the reporter. Sorry, reporter, we're both wearing wet clothes now. All right, and then the last one is when you were going around the corners, when you turned, what happened to the water? So when you turned to the left, which way did the water go? Well, it stayed where it was, maybe moving forward, but you basically took the tray out from underneath the water. So the water kind of kept going straight and then started to fall because there was no tray holding it up any longer. So gravity pulled it down to the ground. So as you turn to the left, the water, based on your perspective, seems to go to the right. It doesn't really. It continues going straight, but you've turned, so your frame of reference has changed. So the water keeps going straight, but it seems like it's going to the right because you've turned to the left. Okay? Likewise, if you were to turn to the right, the same thing happens, but in the opposite direction, right? So you turn to the right, and it goes to the left. Or actually straight, but it seems like it went to the left because you've turned and now it's off to your left instead of being in front of you. Okay? So that's what you should have, those were your answers that you should have gotten on your worksheet in the scenario. So let's go ahead and look at some everyday applications. So there are a lot of applications of Newton's first law of motion. And by watching the video, you've already considered some of your experiences in a vehicle, in a car or a truck. But have you ever observed the behavior of coffee in a coffee cup filled to the rim while starting a car from rest, or while bringing a car to rest from a state of motion? The coffee keeps on doing what it's doing. Let me tell you a little story. It's kind of funny now, but it wasn't funny when it happened. But my family and I, when I was growing up, we always used to go down to some relatives down in Maryland and stay for a week with them. And we'd go out to the bay and go crabbing, and we'd ride horses. They had horses on their little farm, and so it was really awesome. It was a great vacation we took every summer. Well, one year we were leaving, and my father placed his coffee cup up on the dashboard of the car, kind of right in front of the steering wheel. So, heads up, my dad kind of had a short temper when he was younger. When I was growing up, he had a pretty good temper. But anyway, he takes off, right? He hits the accelerator in the car takes off. This is one of those great big station wagons with a V8 engine in it, which is a big engine. The car takes off. The coffee cup that was at rest while the car was not moving wants to stay at rest. So the car kind of pulls out from underneath it, and the coffee begins to tilt, and all the hot, steaming coffee lands right in my father's lap. Well, needless to say, that triggered his temper really badly that day, and he had a few choice words to describe what he was going through. I'm not going to share those with you, it'd be inappropriate. But needless to say, had he only remembered his physical science class from high school, where he learned about the laws of motion, he probably would not have placed his coffee cup on the dashboard and then hit the accelerator in the car. So, lesson learned. All right. So, here's a little GIF. Shows you the law of inertia, which is another way to say Newton's first law of motion. But the law of inertia is very commonly experienced when you're riding in a car or truck. In fact, the tendency of moving objects to continue in motion is a common cause of a variety of transportation injuries. Both small and big accidents are examples of this. So consider, for instance, the unfortunate collision of a car with a wall like we see here in this little animation. As soon as the car hits the wall, the unbalanced force acts upon the car to abruptly decelerate it to a resting point. So it goes from being in motion to being at rest. But any passengers in the car will also be accelerated as long as they're strapped into the car by the seat belts. Bam! That's inertia. All right, so there are lots of other applications of Newton's first law of motion as well. So you've already considered the automobile. We've talked about the behavior of a coffee cup that's filled to the rim and what happens when you take off from a position of rest, and then what would happen when you bring the car back to a state of rest from a state of motion. Coffee just keeps on doing what it's doing. So when you accelerate a car from rest, or when you bring it back to a point of rest, the road provides an unbalanced force, and the brakes also apply an unbalanced force. So that's where our net forces are coming from. Here's another everyday application. So when you quickly stop while you're riding or descending on an elevator, when you're going up or you're going down, the blood rushes from your head to your feet when you go up, and it rushes from your feet to your head when you go down and you stop suddenly. So if you've ever felt that kind of queasy, almost dizzy feeling when you're riding on an elevator and it stops suddenly, it's thanks to Newton's first law of motion, or maybe not thanks to Newton's first law of motion, but he has been able to describe for us what's causing that. So here's another everyday application. You've got this hammer, and it can be tightened onto the handle by smacking the hammer handle, the end of it, on a solid surface. So if you set the hammer head on top of the handle and just get it on there lightly, and then you start hitting the hammer end, the end of the handle part on the desk, that sudden stopping will cause the head of the hammer to lodge itself further onto the handle. I don't know if you've ever done that. We used to have axes when we were kids. We'd have to chop wood, and we had these axes, and they'd get old, and the head would come loose and would come flying off. You had to be very careful. You didn't want to kill anybody with the head of the axe flying through the woods. So we would have to bang the handle on the ground to reseat that axe head on the handle so that it wouldn't come flying off when it got loose. So we'd have to pay attention, look for it getting loose, and then do that process again. And we didn't know it at the time, but we were actually taking advantage of Newton's law of motion. Another one is a brick is painlessly broken over the hand of a physical science teacher by slamming it with a hammer. Caution, don't try this at home, especially if you know a physical science teacher. And don't come here and try it with me. I'm not going to put my hand underneath your brick. Alright, sometimes when you're trying to get ketchup out of a bottle, especially a glass bottle, the squeeze bottle's kind of eliminated this problem, but back when we always used, or I should say back when ketchup always came in a glass bottle, sometimes it would get stuck. You couldn't get the ketchup out, so you had to turn it upside down and you'd have to hit the bottle. So it would cause the bottle to move forward and then suddenly stop, and hopefully the ketchup inside would continue moving. And then end up on your sandwich or wherever you're trying to apply the ketchup. And also headrests are placed in cars, and the reason they're there is because of Newton's first law of motion. These are to prevent whiplash and injuries during rear-end collisions, because you remember the guy in the video talking about your head would stay stationary as the car kind of gets pushed forward by the other car ramming into the trunk of your car. So the headrest prevents your head from snapping back, which would cause an injury in your neck. So the headrest is a safety feature to try to overcome or compensate for the laws of motion. When you're riding a skateboard or riding in a wagon, I don't know if you've ever jumped in a wagon and went flying down a hill, seemingly out of control, probably out of control, or when you ride a bicycle, when you hit a curb or a rock or some other object that can apply enough force to your motion, you tend to keep flying forward, and your vehicle, whatever it is, your skateboard or your bicycle or whatever, tends to all suddenly stop and stay where it is. We call this an endo. I love mountain biking. I go out mountain biking a lot. And sometimes, if I'm going over a big log or something, that log will stop the bicycle's forward momentum, but my forward momentum will take me right over top of the handlebars. Not a good day. In fact, I think I tore my rotator cuff this summer doing that very thing, and it still hurts to this day. So I should probably go see a doctor and maybe get some surgery on my shoulder, or some physical therapy or something. I don't know, but it hurts every day. Anyhow, I digress. So for our exit ticket today, you're going to give an example of Newton's first law being applied. But you have to use an example that hasn't been used in any of today's materials, none of the videos or this presentation. Come up with your very own example for your exit ticket. All right, thanks.